All right, so today in the penultimate chapter, we're going to cover classes of photoluminescent compounds. So we've gone through a lot of theoretical aspects of photoluminescence, and then a little bit on experimental techniques and how to measure it. And then today we're going to dive more into the chemistry and talk about different types of molecules and materials that would exhibit photoluminescence, and a little bit about their structure-property relationships. All right, so the first type we'll talk about are conjugated organic compounds, and which should be fairly intuitive to most of us by now, is that these would be compounds that would typically luminesce via fluorescence primarily. So they almost always have closed shell ground states. There are examples of open shell organic radicals, and some of them have exhibited luminescence, but the vast majority are singlet ground states. And as I'll show you in some of the specific examples, they can be as simple as aromatic hydrocarbons. And obviously some people in our group are familiar with that because of, we have pyrene as an example of something that would be a fluorescent aromatic hydrocarbon. But many classes of organic compounds are fluorescent, and they often have substituents or other heteroatoms in the structure that can sort of diversify the properties. These types of compounds are usually studied in solution. So again, we mentioned before different ways of measuring photoluminescence, and for most organic compounds, they're done in liquid solutions. But there are examples of films and other architectures that are sometimes important. Now, to talk about the types of orbitals that are involved in the excited states that are thus generated, the singlet excited state S1 pretty much is, in most cases, can be thought of as just a simple homo-lumo transition. And because these are conjugated organic molecules, that would represent a pi-to-pi star type excitation. So from a bonding pi orbital to an anti-bonding pi star, and that's usually going to give you your lowest energy excited state, and that would be often where fluorescence comes from. Now, there's also some variation on this. In particular, if you have heteroaromatic compounds or compounds that have certain types of substituents that would have non-bonding lone pairs involved, then you can have what are called N to pi star transitions. These are not as frequently observed in fluorescence, but they can be, and that's where the N, as is abbreviated, would be referring to a non-bonding or lone pair type orbital that's initially populated. Another thing about organic compounds is that in most cases, there are exceptions to this when we talk about TADF materials, which we've covered a little bit in the past, but most conjugated organic compounds have large single triplet gaps and pretty minimal spin-orbit coupling. So that is, again, the reason why you're going to see pretty much only fluorescence. If there is phosphorescence, it's usually very weak, often only observed at low temperatures, and it would have very long lifetimes, usually milliseconds or longer, if you're talking about an organic compound. So those are going to be some of the key features of organic compounds. And so because they emit via fluorescence, these are the types of compounds where you're most often going to see that nice sort of mirror image and overlapping between the absorption and the emission bands that we talked about before, and how that can allow you to determine E00 and other things. All right, so one thing that I want to recommend to you is this resource for looking up photoluminescence data. I don't know if any of you guys have played around with this before. It's useful for, if you need a new quantum yield standard, if for some reason your favorite one's not working out, or if you just want to look at, whatever kinds of compounds you're working on. It's mostly organic, so this is it has some things like rubipi and things like that, but I don't think it has a ton of organometallic compounds. So there's a paper about it, and there's the link, and it looks like, I've never tried actually downloading. I don't know if the downloaded version has more features. I usually just search it on the website, and you can export the data. You can, it'll usually show you the quantum yield for things that are fluorescent and what the spectra look like, absorption and emission. So it's pretty useful. It was designed by Jonathan Lindsay. I don't know if any of you know who he is. He's at NC State, so I guess our old friend Michael might get to know him a little bit. But Lindsay is a porphyrin chemist, so this is pretty much, if you look at like their recent updates, chlorophylls, whatever tauloporphyrins are were added. So it has all kinds of macrocycles like that, but it has other classes as well, including stuff that we use both as references and things like coumarins and possibly bodipes that we would actually potentially work with. So that's useful, and I want to recommend that because a lot of the spectral data that I'll show today comes from that. So it's not stuff that obviously we collected on our own. I got it from there or from papers sometimes. Okay, so let's go into how the fluorescence works in aromatic hydrocarbons, and it's a pretty simple relationship involved here, which is that as you increase the conjugation length, as you make it more and more conjugated, you tend to shrink the HOMO-LUMO gap. That should be a concept we're pretty familiar with. And then when you do that, you redshift the fluorescence, because again, the fluorescence typically involves a HOMO-LUMO type excited state. So benzene itself is fluorescent, not particularly strong, and only in the UV. So if you're working with benzene as a solvent, or toluene, which is very closely related, make sure you don't excite where the solvent itself absorbs, and you would see some emission, although again in the UV region where we're not usually looking ourselves. So benzene shows up there, and if you increase the conjugation length in a sort of just a linear fashion through the naphthalene, anthracene, tetracene, pentacene series, you can see that the spectra progressively redshift as the HOMO-LUMO gap shrinks. So that's increasing ring conjugation size from, again, 1 to 5 rings as I'm showing here, and the shift goes further and further, and most of them have modest to decent quantum yields. You'll notice in all of these spectra you have pretty sharp vibronic structure. I believe these are all room temperature spectra, so this is not even at low temperature that you'll see this type of vibronic coupling. And the spacing between those is on the order of 1400 wave numbers, which is usually what you'll see when you have fluorescence or phosphorescence involving aromatic moieties, and that's going to be consistent with the aromatic CC stretching vibration being the vibration that's coupled to the electronic excitation. So that's how those work. And then you can also extend the conjugation in the other direction. So the previous series, again, was extending it in what we call the X direction if we're doing it horizontally, and then this would be adding conjugated constituents at a 90-degree angle to the main core. So if we start with anthracene, which was also on the last slide, you can add phenyl rings, which redshifts it to some extent, or you can add this phenylacetylene type constituent that would redshift it further. So again, the same story is true. As you make the conjugation, the pi system longer, you tend to get fluorescence further and further into the red. These ones are not as dramatic as the last ones, but still going from UV to blue fluorescence into the sort of blue-green region, so it's a pretty significant shift. And for reasons that I probably don't have a good explanation for, these substituted ones here, where you put substituents on those two positions in the anthracene core, also have exceptionally high quantum yields, unity as they're reported. All right, so then we're going to talk about another kind of organic compound called laser dyes. Now there's a ton of these, so I'm not going to give too many examples, but if you go to that database that I referred to, it has a lot in this category. And a laser dye is sort of the general name for a wide range of highly fluorescent organic molecules that are used in dye lasers. So that's one type of laser. I feel like dye lasers aren't used as much anymore, but I'm sure in some settings they are. So
Thoughts most lasers were like semiconductor and like crystals.
So the ones they use now, the ones I'm most familiar with are like titanium sapphire and neodymium YAG, which would be like a doped solid state type laser. So, but there are dye lasers that I've heard. I think there's also ruby lasers. We'll talk about ruby a little bit later on. So, but anyway, these have been used in lasers, and they're even if they're not commonly used for that anymore, they have really high quantum yields and they have good stability, which is why they're able to be used as a lasing medium. And so they have, there's two common cores that are found in laser dyes. Of course, there are others, but the coumarin core that we're all familiar with, and then xanthine is another core. Xanthine itself, I don't think is very fluorescent, but there's a bunch of substituted analogs of xanthine that in a huge category of those that do have very good fluorescence properties. So this is what a few examples of them look like. So most of these laser dyes annoyingly have trade names that don't really tell you anything about the structure. So this is coumarin 1. Don't ask me why. I don't know if that means it's the first coumarin that was ever made, or someone decided to number it as number 1. So that one is blue fluorescent and has a 50% quantum yield. And then the fluorescein is an example of a xanthine dye, where the xanthine core is partially oxidized, and you have this other constituent there. So that one has close to 100% quantum yield in the green region. And then rhodamine B, which I stupidly used as a quantum yield standard once for a compound that had like a 1% quantum yield. So that was a dumb move. But anyway, it has a quantum yield of about 70%. It is a pretty good quantum, and all these would be good quantum yield standards, but again, they all have high quantum yields, so you wouldn't want to use them for something that has really weak emission. But anyway, this is rhodamine B, which also has the xanthine core, but this time with dimethylamino substituents, and that gets you a little bit more of a redshift. I think this one's yellow if you look at it in solution under visible or UV excitation. So those are examples of laser dyes, and you can basically find those that have pretty much any color you want, and most of them are commercially available under these different trade names that they're marketed as. So those are another class of organic compounds. Now the type that I guess none of our guests are here today, so this is probably useless for you guys, but the other type of luminescent molecule that we'll discuss right now are phosphorescent coordination compounds, which are in many cases the classes of compounds that you guys work with in your research. And first I'll just show some, again, general principles of how the photoluminescence in these works, which you guys, again, are probably mostly familiar with. These are also compounds that typically have S0 ground states. We're going to talk about one type of coordination compound later where that's not the case, but for most of the ones that have conjugated ligands around them that are responsible for the chromophoric behavior, they're usually single ground states. But in this case, it's not typically fluorescence that observed, but phosphorescence from a T1 excited state. So to have phosphorescence, as we discussed in an earlier part of this course, there's going to be 2 spin-forbidden processes involved. So first, because we're starting with a single ground state, you typically have to do intersystem crossing to get to T1, because you're going to typically excite from S0 to S1 and then intersystem cross to T1. So that has to happen. And then once you're in the T1 excited state, to get phosphorescence, you have to go back to S0, and that has to happen in a radiant fashion. So that's also spin forbidden. So there's 2 spin forbidden processes that have to occur. And the reason that they occur in these types of compounds is because they are greatly accelerated by virtue of spin orbit coupling. So we're not going to go into a lot of the details. We had a whole separate lecture on spin orbit coupling a while ago. I think that was after you left.
I went there too.
Oh, you did? Okay, so that was a while ago. But so we talked about spin orbit coupling from a symmetry standpoint there. But from the standpoint of luminescence, why it's important is that it accelerates those spin forbidden processes, because the spin orbit coupling is proportional. I think it's not just Z, but it has some direct dependence on Z, which is the atomic number of the metal nucleus that's involved in that. So because of this, most phosphorescent compounds have 4D or 5D transition metals. You need a relatively heavy metal center for that to occur. And then in terms of the general structural elements that you'll find for these compounds, it's usually going to have the metal surrounded by one or more conjugated ligands. There are examples of bimetallic compounds that are phosphorescent as well, where you can have metal-metal bonding or antibonding orbitals involved. But usually it's going to be a single metal center, which would have valence d orbitals and one or more conjugated ligands. And so the valence d orbitals are usually partially occupied. Most of the phosphorescent compounds are, D6 or D8 is probably the most common d electron count for phosphorescence. You do have some examples of D10 where you wouldn't have the d orbitals directly involved in the excited state necessarily, but you still have MLCT states from those. So a wide range of d orbitals, because these are usually 4D or 5D metals, and because they have singular ground states, you're talking usually D6, D8, D10 being the most common. The excited states usually have considerable charge transfer character because, again, the valence filled orbitals, those that are close to the HOMO level, usually involve a lot of d orbital character on the metal. and then what you're exciting into, which is either the LUMO or some other higher lying accessible orbital, is going to be pi star on one of the ligands, and so you have that charge transfer from the metal to the ligand often being invoked. And then if you want to tune the phosphorescence in one of these compounds, that can be done by either changing the metal and or the ligand. So if you look at a series of compounds that has the same ligands with different metals at the center, you'll see differences in phosphorescence by virtue of changing the metal, and you'll see the same thing if you alter the ligand, which is the much more common approach, I would say. All right, so here are some common classes of phosphorescent coordination compounds, which again, most of these you guys are very familiar with. So the sort of the world's favorite or longest standing photoactive molecules are these, especially rubipi with ruthenium at the center, or the osmium analogs are pretty well known as well, where you have, I'm just showing sort of the simplest core structures. Of course, you have many substituted analogs or analogs that have extended conjugation on one or more of the ligands, all kinds of variations, but this has been studied really since probably at least the 1950s. And it's not, they are phosphorescent, they're not really best known for their phosphorescence attributes. They're mostly known for their photochemistry, being able to transport charge from the excited state, but they are phosphorescent, and they're widely studied in a lot of different contexts. There's a class of rhenium compounds that are reasonably phosphorescent as well. These are also strong photooxidants if you're working in that area. So they would typically have something like a bipyridine as a chelating ligand, facial arrangement of 3 carbonyls, and then a variable L ligand, which is often a neutral donor, making them cationic. This L could also be an anionic ligand. They have neutral analogs of these also, but it's some sort of monodentate ligand that occupies that last coordination site. So those are phosphorescent. We're not going to really talk about those in detail. The ones that we all know about, and that I do have a figure in the book on, so I'll show it to you here, though it's not going to be surprising to any of you, are these cyclometylated iridium compounds. So I'm not going to, I guess there might be somebody watching the video that doesn't know what these are. So anyway, they look similar on the surface to the rubipi, but they have organometallic monoanionic chelating ligands, which involve each of them in one of these iridium carbon bonds, usually to a phenyl ring or some other simple aryl group. And so there can be a few structure types that are common within these. So the homoleptic compounds, usually with the facial arrangement of the ligands being the one that's most thermodynamically stable, so the one that you'll typically observe and that has usually the best phosphorescence attributes. The heteroleptic compounds that are bis-cyclometylated, so 2 of the cyclometylating ligands and 1 of something else, often an ACAC in the context of especially OLED compounds. And then these cationic analogs where you have the 2 extra coordination sites occupied by a bipi or something similar to that, again making it overall +1 charge. So those are 3 common classes of those. Another one that is related to this, these were studied a lot when cyclometylated iridium compounds first became so popular. They don't seem to have found as much traction as them, so there are not as many papers on these anymore, but there are cyclometylated platinum compounds that have the main difference, of course, being that these are D8 square planar as opposed to D6 octahedral. So now you just have either homoleptic compounds with 2 cyclometylating ligands, or the ACAC compounds that have 1 of each, a cyclometylating ligand and an ACAC. Their sort of trends and behavior are kind of similar to the iridium analogs. And then another class of platinum compounds that our group is familiar with are these platinum acetylides, which can also have a variety of structure types. So some of them would have a chromophoric ligand like a bipi, and the acetylides more or less just serve as ancillary ligands. And so that would be one class here, where usually the excited state in these compounds would be a charge transfer state involving the bipi or whatever other type of chelating ligand you have. But then the type that our group often works with, or that we are even more familiar with, have these monodentate L-type ligands with the acetylides at the other positions. In this case, it's actually the acetylide itself that serves as the locus of the excited state. Usually more of a pi to pi star state, but some sort of charge transfer character is often involved as well. So those are common classes of phosphorescent coordination compounds. There are many others, but as I said, it's usually 4D and 5D metals. and as I said, D6 and D8, all these are D6 or D8. Those are the most common D electron counts. All right, so again, something that I don't need to show the people in this room, but this is how the phosphorescence behavior works in these common cyclometylated iridium compounds. So this 2-phenylpyridine is the sort of simplest, I suppose, of the cyclometylated ligands that's used. It was done in used in a lot of the earliest studies. And so when you have these types of compounds, the color of the phosphorescence is dictated by the choice of cyclometylated ligands. So the excited state is going to involve considerable metal to ligand charge transfer character with the iridium 5d orbitals being strongly involved in the HOMO, and then the pi star on the cyclometylated ligands being the orbital that you would promote the electron to in the excited state. So with phenylpyridine, you get green phosphorescence centered around 520 or so, and then you can blue shift or red shift that by changing the structure of the cyclometylated ligand. So the common way of blue shifting is by adding electron withdrawing groups, particularly to the aryl ring. So this very common F2PPY that we all know about causes the phosphorescence to shift to the blue of what it is in the parent compound. And then the rest of these modifications, if you replace the aryl ring with something more electron rich like a thiophene, that causes a red shift. So this trace in orange here, that's sort of a yellow-orange emission color. And then if you increase the conjugation on one or both of those sites, so either on the N-heterocycle or on both, on the aryl ring and on the N-heterocycle, those are both common strategies for shifting it further and further into the red. So we can, with this same structure class, go from the blue region. There's probably even analogs that emit in the UV, although not particularly well, but then you can shift all the way to the near IR just by changing the CN ligand. So it's quite a versatile system for being able to have phosphorescence wherever you need it to be, and most of these have pretty good quantum yields and things too, which is why they're so widely studied in the literature and in industry. All right, so that's how those work, which we're all familiar with. So now we're going to get into some classes of compounds that we don't talk about nearly as much in our group meetings, in our research. And so the first is going to be another type of coordination compound where the emission comes from a DD excited state. So those of you that took my course learned all about DD excited states. We talked about Tsunami-Sugano diagrams and things of that sort for understanding those. And those DD excited states are very commonly studied in the context of UV-vis absorption. So if you look at most transition metal compounds, when they're dissolved as aqueous solution, simple salts especially, they would have coloration that is caused by these DD transitions. But in most cases, the DD transitions are not going to be luminescent. So these ligand field transitions are most commonly studied in octahedral metal complexes, and the type that we'll talk about in more detail have approximate OH symmetry as well. And then in that case, the d orbitals split into a T2G and EG set, triply degenerate and doubly degenerate, and the DD transitions involve promoting electrons from T2G to EG. So as I said, these types of transitions they give rise to color in many transition metal salts when they're dissolved in solution or as ionic compounds. And so there's a lot of UV-vis studies on those, but they're much less common in photoluminescence. And then in terms of how many excited states there are, they can be rather complex in most cases. So if you have a D1 or a D9 ion, something like titanium-3 or copper-2, in those cases you just have one excited state. So you'd have a ground state of doublet multiplicity and an excited state of doublet multiplicity, and it's a simpler situation in that case. But when you go to d electron counts of 2 through 8, which there are examples of all of those, you have many possible excited states, some of them excessively complicated. So in terms of which excited states are involved, that can be sometimes a bit of a chore to figure out. If you looked at Sugano diagrams, you know how complex they get for some of these electron counts. Now, in terms of when you would see luminescence from a DD transition, as I said, it's not very common, but there is one that you may have encountered in your everyday life, which is chromium-3. So chromium-3 is a D3 metal ion, and it would have octahedral coordination. And if you've ever looked at ruby, they have that sort of red sheen to them, and that's not just the color of the ruby, that's actually luminescence coming from the chromium-3 that's in the ruby. So ruby is I'm not going to give the detailed structure, but it's basically a metal oxide doped with chromium-3, and those chromium-3 sites in ruby are luminescent. So the way that they luminesce, the way that chromium-3 luminescence works is that these are D3 compounds. So in the ground state, you have a T2G3 configuration, which gives rise to a quartet A2G ground state. Something else we talked about a long time ago is that usually for DD transitions, you're going to use Mulliken symbol labels for all the ground state and excited state terms. So you'd have a quartet A2G ground state. You have two quartet excited states that are accessible with visible excitation. I think for ruby, it's around like 400 to 500 nanometers you can excite, and you would get absorption bands associated with those. They're still not particularly intense absorption because these would be electric dipole forbidden, but nonetheless, the excitation is going to involve population of higher lying quartet states, but you don't get emission from there. You get intersystem crossing down to two closely spaced doublet states, so doublet T1G and doublet EG that are much lower in energy. And then you'll observe that red phosphorescence that comes from ruby is the decay back to the ground state from really both of these doublet states. As you'll see, there's two closely spaced emission bands, one for each of these. So it's not vibronic structure in this case, it's actually two different electronic states that are really close to each other. So here's what the photoluminescence of ruby looks like. It's very sharp because you don't have, it's a solid state material. We'll talk about another class of solid state materials a little bit later. So you don't have solvent causing line broadening as you do when you study things in solution. You don't have any vibronic structure or any charge transfer states involving ligands. So you get very sharp bands in ruby. And again, there's two of them because there's two doubled excited states that are close together that both decay to the quartet ground state. And natural ruby has an exceptionally long lifetime of 4.3 milliseconds. And this would be classified as phosphorescent. It's not the typical T1 to S0 phosphorescence that we see in the vast majority of cases, but it does involve a radiative transition where the two states have different spin multiplicities, doublet and quartet, so that classifies it as phosphorescence. So ruby is just a chromium-doped aluminum oxide material, so it doesn't have a particularly complex structure, but it does give that nice red emission from the chromium center. Now there are also synthetic analogs of ruby, and so this one was, I don't have the reference here, I should have. This one was prepared, and the person who kind of pioneered this work is Katja Heinz at Johannes Gutenberg. Did anybody here work with any of the German exchange students, or was that before your time? Some of you guys
didn't work with them, but
you know who they were. Yeah. So she's at the university that they come from, and one of our former German students, Stephen, is now in her group. So anyway, as an aside, that's where these compounds come from, and they have very similar features as natural ruby, but again, these are studied in solution, so they have broader emission bands as you normally see in solution, but they have the same two electronic transitions, the doublet T1G, the quartet A2G. This is, of course, a little bit distorted from perfect octahedral, but it's close, and so you see the same types of transitions, a little bit redshifted because of the different ligand field of these pyridyl-based ligands compared to the oxide ligand field that ruby has. And so you can make synthetic analogs as well. It's hard to get them to have really reasonable quantum yields because, again, these have really slow radiative rates. Most DD transitions, as we said, aren't luminescent at all, but you can design these ones to have lifetimes close to a millisecond and quantum yields of 12%, which is pretty decent for that part of the spectrum. All right, another class of coordination compounds, and also you'll find these in solid state materials as well, would be those that are based on lanthanides, the F elements. I guess actinide is possible as well, though those are typically radioactive, so they're not studied nearly as much.
Looks like some uranium, but it's like the uranium like dication mostly.
Okay, yeah, so I think Gail talked about
It's
that.
like uranium and like thorium, and the rest of them are like not naturally occurring enough for people to really care.
Yeah, well, there's groups that care, but they have
Yeah.
you have to have very high security clearance,
Yeah.
and you get like milligram amounts of them, so it's challenging research that most people don't want to take part in. But anyway, the lanthanides many of them are luminescent in both coordination compounds and solid state materials. So they usually involve the ions in the +3 oxidation state. I'm not don't know if I have a good reason for why that is, but the lanthanide ions typically have their most stable oxidation state being +3. And so they have different F electron counts depending on what their identity is. And the coordination geometries are often more complicated than we're used to as well. So they're variable, and a lot of times they have coordination numbers greater than 6 in these lanthanide compounds. They have much larger ionic radii, so they can accommodate more ligands than you typically see in a transition metal compound. Now that said, even though the coordination geometry is variable, and even though there's lots of different types of ligands that can be used to support these, you usually have very weak interactions of the f orbitals with the ligands. And so when you look at the frontier orbitals in these compounds, the ones that are involved in luminescence in particular, they're pretty much pure 4f orbitals if we're talking about the lanthanide series. So they don't have very much mixing with the ligands, and that also means, as we'll talk about as well, that the luminescence doesn't really change much if you change the ligand. It's mainly going to be dependent on what the identity of the metal ion is. And so because these frontier orbitals have very little mixing with the ligands, people still use atomic term symbols to describe them. So they don't use molecular term symbols or any other descriptor. It's just going to be the pure atomic term symbol of what you would have for the free metal ion as well. Lanthanide compounds are even heavier than transition metals, or than most transition metals anyway. So they have large spin orbit coupling values, and so the splitting between J values is significant. So many of the transitions that you'll see involve the same electronic term but different J values, and those are spread by quite a bit in these types of compounds, so they're easily resolved. And so in these compounds, you'll have sharp emission bands as well, and that's again in large part because you don't have very much mixing of the metal orbitals with the ligands, and you can predict where those emission bands will be based on the identity of the lanthanide ion. They don't shift around a lot, even if you change the coordination geometry, even if you change the type of ligand. So they're pretty much only determined by what lanthanide ion that you have, and there's pretty much no vibronic structure, because again, that vibronic structure would require coupling with the ligands that's just not existent in these types of compounds. Now, even though the ligands don't affect where the emission occurs, they can be very important for sensitizing the luminescence. So we'll talk a little bit about the sensitization mechanism that many of these compounds have. And so the reason that you need this type of approach in most lanthanide coordination compounds is because the FF transitions themselves, if you're trying to just excite one of those transitions, just like DD transitions, they're electric dipole forbidden, and they have very low oscillator strength, very low absorptivity. So, lanthanide compounds, even though they can be luminescent, they don't absorb very well. And so the way that you typically design these compounds then is you use some sort of a conjugated ligand to support them, which at least would absorb UV light if nothing else, possibly even into the visible depending on the nature of it. And so you basically have a chromophoric organic ligand surrounding it. You absorb into an excited state that's localized on that ligand. So that's what this singlet L star represents, some sort of usually pi to pi star state on that ligand. And then because of the heavy lanthanide ion that's present, you will still see intersystem crossing. So the singlet excited state on the ligand will intersystem cross to a triplet. But then before luminescence can happen from here, if everything's designed properly, you'll have rapid energy transfer to the lanthanide ion, and then that will generate the excited state on the lanthanide, which is again some sort of FF transition. So it's sort of an energy transfer cascade or intersystem crossing followed by triplet or other types of energy transfer depending on the nature of the lanthanide ion. But that gets you then to an excited state on the lanthanide, and then from there you see the photoluminescence. So the sensitization is basically designed to make sure that you absorb more photons, so that you don't, it doesn't change the inherent quantum yield of the lanthanum ion, but it just changes how many photons are absorbed, which then changes the brightness relative to a compound that didn't have that type of sensitization going on. All right, so that's how sensitization works, and so here's just a diagram that shows what the typical photoluminescence spectra of lanthanide complexes look like. The ligands are not specified. I don't even know if the source that I got this from said what the ligands were, but again, it doesn't really change much anyway. So, if you have the one that's in purple is neodymium. So if you have a neodymium compound with any ligand type, you're going to expect to see these three bands all in the near IR for neodymium, but they're not going to move around a lot as a function of ligands. And you can see that some of them emit primarily in the visible range, so the dysprosium dy and samarium sm have primarily visible emission, as does, I guess that's probably terbium, Tb. But then a lot of lanthanide ions also emit deeper into the near infrared, which has, important applications outside of things that we normally talk about, but things like telecommunications and other imaging type approaches that use near infrared. So they can emit throughout the spectrum, and many of them have more than one emission band, and we'll talk in a second about why that is. So if you want to assign, then we have multiple peaks in the spectra, and in most cases, and you want to know which term symbols are involved. There's a diagram called a Deke. I don't know if I'm pronouncing it right. Deke diagram, or Deka. It's probably German. So anyway, these are diagrams that summarize the energy levels of all atomic states for the lanthanide series. So they're kind of like Tsunabe-Sugano diagrams, but they don't have a horizontal axis, because in Tsunabe-Sugano diagrams, the horizontal axis is ligand field strength, and it shows how the energy levels change as you change the ligands. That doesn't really happen in F-element compounds. So it's just a vertical stacking of all the different energy levels that are present in a given lanthanide ion. So it'll have the ground state as the lowest one, and then all the different excited state terms above that. And then there are selection rules that I'm not going to cover here that determine which transitions are most likely observed. But again, the energy of those transitions is very predictable based on the identity of the ion. And so using the Deka diagram, we're just comparing to other compounds of that same metal ion. You can determine which transition is which, usually in a pretty straightforward fashion. So here's an example of that. So this is a europium-3 complex, and this is one that would have 8 coordinate geometry. So it has 3 of these substituted ACAC ligands, and it also has a phenanthroline. And so one or both of those ligands would serve as the sensitizing ligands that would absorb strongly in probably the UV regions mostly, and then sensitize the europium center. And so the way that this emission works in europium-3 is that you have a 4F6 valence configuration. So it's an F6 ion, which gives rise to a septet ground state. So the ground state for europium-3 is septet F0. And then all of the luminescent transitions in this compound occur from the same excited state, which is a pentet D0, where again that subscript number is the J value that's associated with it. We always have to designate J values because they do split quite a bit. But then what happens is from that excited state, it's going to relax to the ground state, but terminating at different J values within that septet F ground state. So this one here goes all the way to the ground state, and that's the highest energy peak that you see. But the most intense transition occurs when it terminates at the septet F2. So it's a same term symbol as the ground state, but a different J value. And you can see that those two peaks are separated. This one's probably about 560 for that one, and about 620 for that one. So you're looking at a 60 nanometer difference, which is probably at least 1,000 or so wave number, probably more than that, probably a couple thousand wave numbers or more, just because of different J values. So the J values span, you span a range of peaks from 560 to over 700 just by virtue of changing the J value. And so all those peaks represent different J values that it terminates at. And so that's going to be what F-element spectra look like. Sharp peaks, usually multiple peaks, and large splitting between J values, which is often why you see many peaks involved. It's a more complicated excited state manifold. All right, we're going to move on from molecules now, and the last couple things we're going to talk about are either nanomaterials or extended solids that are luminescent. And so one category that behaves, or they're studied a lot in the same way as molecules are, usually studied in a solution. They're not really soluble, I suppose, but they're dispersible, at least in a sort of homogeneous manner. So you can study them in solutions, and that's often how they're approached, are called quantum dots. So what a quantum dot is a semiconductor nanoparticle. It's just another name for it. And usually the word quantum dot would be used for one that has a spherical shape. You can prepare nanoparticles that have all many different types of shapes, depending on the synthesis conditions and the material that you're using. And some of those oddly shaped nanoparticles are also luminescent, but most of the luminescent ones that are studied and that are used in all kinds of applications like bioimaging and even TVs now. If you have a QLED? those are typically spherical dots as far as I know, although the companies don't tell you what they use, but I'm assuming that's what they are. So they're semiconductor nanoparticles, usually spherical, and as the name nanoparticle implies, they're on the nanometers length scale. Usually 1 to a few nanometers is most common. Now, these quantum dots are always going to be stabilized with surface ligands, which can be of several varieties: phosphines, phosphine oxides, amines, carboxylates, sometimes polymer-based ones that sort of wrap around the particle. Those play an important role in stabilizing the particle and dispersing it into whatever medium you want to disperse it into, and ensuring homogeneity in terms of size and all that stuff. They don't really affect the emission, but they have an important role on stability, so they need to be there. And the photoluminescence in these compounds involves radiative recombination of an exciton. So way back when, probably chapter 2 in this book, we introduced the very simplified diagram for how excited states are produced in semiconductor nanoparticles, where you have a valence band and a conduction band, and excitation with light promotes an electron from the valence to the conduction band, and it's really just relaxation of that electron back into the valence band that causes photoluminescence. You can sometimes have dopant states, and you can sometimes have trap states. If you guys ever studied quantum dots in more detail, there's a lot wider variety than just exciton emission, but exciton emission is the most common, and it's the type that's used in many of the applications that we talked about. So that's how emission happens. Now, the thing that's interesting about quantum dots is, even for a given material, though, you might think, well, if it's the same material, it's going to have the same band gap, and that would be true in the bulk. But because of quantum confinement, the band gap is dependent on the size of the nanoparticle. So as you have a single material and you change the size, you're going to get different band gaps, which then result in different photoluminescence wavelengths and colors. So it's very tunable based just on the size. And so that's how it works for quantum dots, and that's one of the reasons they're valuable, is that you don't need to change the composition or change the ligands or anything like that. You just have to change the size, and they're very good, very reliable synthetic techniques for doing that, although how reliable those are, I guess, is in the eye of the beholder. So anyway, so here's an example of quantum dot emission. This is cadmium selenide, which is the most commonly studied one, and it shows some of the sizes here. So these are going to be cadmium selenide quantum dots that range from 2.1 to 7.5 nanometers. So relatively narrow range of sizes. And as you can see, the emission can be tuned all throughout the visible range just by changing the size. So at about 2 nanometers, you get blue, and about 7.5 nanometers, you get red. And as far as I know, cadmium selenide is the type that's being used in the QLED TVs. Although it may be something else that's proprietary, I don't know. But these have been studied to death, basically. This is the most...
They got bad from Europe in like 2019.
Yeah, they did.
Because of cadmium poisoning?
Yeah.
So in California, too.
Are people eating their TVs?
Yeah, that's what I was saying, yeah.
It was like something about like improper waste disposal. Like cadmium sources leaks.
Yeah, I'm sure there's concerns about that. I mean,
indium like phosphides or something like that.
that didn't stop us from using fluorescent light bulbs for decades with mercury in them. But anyway, so there is a concern. It's interesting that you bring up the concern about the toxicity of cadmium selenide quantum dots, because that, of course, has motivated the pursuit of materials that don't have toxic materials in them. And one of those are called carbon dots. Now, to be perfectly honest, the reason this is in my ebook is because the reviewer asked for it, not because I knew or cared about these at all. I'm assuming that reviewer worked on carbon dots because they were quite adamant that this be there. I would say they're a nice class of materials, but I don't think anybody actually understands how they work. So what I'm showing here, let's just get into what they are first. So they're carbon-rich nanoparticles. So under a microscope, they look kind of like a quantum dot. They're just like usually a circular kind of blob-shaped material. Mostly carbon in the material, mostly amorphous as well. So they don't have a lot of crystallinity either. So it's a little bit hard to know exactly what their structure is at the micro scale level. But they're carbon-rich nanoparticles, and they're prepared by top-down approach. So if any of you ever get into research on nanomaterials, I have a suspicion that these top-down approaches are very finicky to use, and only works sometimes for some people. So what they do is they just take bulk carbon precursors, usually graphite or carbon nanotubes or other types of bulk carbon, and they just blast them, either heat them really high or laser ablate them or something. There's multiple methods for doing this, but basically you just slough off little tiny pieces of carbon under certain conditions, and that'll give you these nanoparticles of usually some sort of size dispersion, but at least in some hands it can be controlled quite well. Now what I'm showing here though in terms of the emission, so these are all typically less than 10 nanometer particles, and they're often passivated by polymers to make them soluble and stable and all that. But these emission spectra here, these are not different size or different composition or different passivated particles. This is the same particle excited at different wavelengths, and I have not found a satisfying explanation for why this happens. So basically, these excitation wavelengths are stepped up from 400 to 600 nanometers. And so as you change the excitation wavelength, the emission band also changes, which, of course, if you saw that in a molecule, that would be very suspicious. In the case of quantum dots, or these carbon dots, that's just how they work. And nobody really knows why. And the proposals that I've seen for why are not very satisfying. And the quantum yield also changes. So these are normalized to quantum yields. That's why they get weaker and weaker as you go further and further into the red. So there's not a lot of insight. Again, the structure of these is poorly understood to begin with, and then in part because of that, and in part because the people that work with them are more application focused, there's not really a great sort of set of principles that determines or governs how this emission works and what exactly is going on. But they are luminescent and they don't have toxic materials in them, so there's been some interest in them. Primarily, I've seen it in biological applications. Obviously, you don't want to put cadmium selenide into living human beings if you can help it, but these would be viewed as a much less toxic analog of those. So there's a lot of work going on with those. I wasn't particularly familiar with them before this reviewer asked me to put them in the book, but they're a cool material and they are sort of an alternative to quantum dots. The last type we'll talk about, which is the type that Jacoa's group works on, if you guys know anybody in that group, are solid state phosphors, which these are going to be extended solids, so they would typically be studied as bulk crystalline or powder in their powder forms. You can't dissolve these materials. If you dissolve them, you break them up into pieces, so they have to be studied in the bulk, and they were usually prepared by solid state approaches also, or possibly solvable thermal methods. Now, just to be a little bit clear about the terminology, when you hear someone from Jacoa's group or anyone in this field describe a phosphor, they're not really referring to the spin of the ground state and excited state, or that it is a spin forbidden transition. In their world, phosphor means long-lived luminescence. It often involves what we would call phosphorescence. Sometimes it's in materials that don't have well-defined spin states, and so you can't really use fluorescence and phosphorescence as extinguishers anyway. And there are probably examples out there of spin-allowed luminescence that just happens to be long-lived and thus would be classified as a phosphor in their world. So they don't use the word phosphor or phosphorescence in the same way that we do, but it does typically mean long-lived luminescence. So we just talked about ruby a little bit ago, so that's one example of a solid-state phosphor where it would actually be phosphorescent. But there are other types that are especially used in things like LEDs, and so there are those LED materials, which are of the type that Jacoa's group studies and many others, are often cerium and europium doped materials. So they also have lanthanide ions in them, although as I'll show you, the luminescence mechanism for those is a little bit different. They don't typically involve FF transitions. They involve a little bit different of an approach. And so the excited state that these types emit from is a 4F to 5D excited state. So all of these are 4F lanthanide ions. That's where their highest occupied orbitals would be. But then in this case, you're exciting into the 5D, the empty 5D orbitals, and the emission then would be the relaxation of that state. So here's how it works. If you have a free lanthanide ion, you would have your 4F orbitals, which would be partially filled, empty 5D. particularly when you're in the +2 or +3 oxidation state, which most of these are. And in the free ion, you have a pretty large separation between the 4f and 5d orbitals, or at least large enough that you're not expecting the 5d orbitals to be populated. But then what happens when you dope this into a solid state material, there's sort of two effects. So one is called a centroid shift. So we already talked about when you have lanthanide ions and you have your 4f valence orbitals, those don't really interact with your ligand field at all. So when you put this into an oxide host, which then exerts some sort of ligand field on the ion, you don't really change the 4f orbitals in any appreciable way. But because of a change in covalency and a change in polarizability of the 5d orbitals by virtue of being in this oxide host, the 5d orbitals would be stabilized. And then also because of ligand field splitting, which or crystal field splitting as it's called for solid state materials, but really the same thing, you get the 5d orbitals splitting. So if it's octahedral, it would just be T2G and EG like we normally see, but they're going to split into 2 or more energy levels by virtue of the crystal field splitting. Again, the F orbitals are not going to be influenced at all by the ligand field, or to a very minimal extent, as we talked about before. So then once you do this, that results in your 4f and at least one of the 5d orbitals being pretty close in energy, and so you can get excitation and emission bands that involve that type of excited state, going from a 4f to a 5d orbital. So a lot of the materials that are studied for LED solid state lighting devices use this type of excited state progression. And so when you have materials like this I think is the last slide, it turns out that the emission that you get is going to be determined both by the nature of the lanthanide ion dopant, cerium and europium, again being the two most common in this context, and is also going to be determined by the nature of the oxide host that you use, because that's going to then change the ligand field, which is going to influence the splitting and the energies of the 5d orbitals that are populated in the excited state. All right, so if you look at these ones here, the blue and the black trace are both cerium doped materials, but they have different oxide hosts, and that shifts the emission quite a bit. And then same with the red and the magenta. Those are both europium-2 materials with different oxides, and that shifts the emission, again, by a large amount, even though it's the same metal ion and the same type of excited state, but you're changing primarily those 5d orbital energies as a way of controlling the energy of the excited state. So the way that we'll talk about applications in our last workshop session, which will be in a few weeks after I get back for some conferences, and in those those applications, these types of materials are used in solid state LEDs, and typically you would want one that covers sort of a wide range of the visible spectrum. So the ability to tune these over the visible spectrum is important for that application. And again, that can be done by changing the ion or changing the host material. So that's kind of the basics of several classes of luminescent materials. I think that's the end. And so I'll stop there and take any last questions you guys have before totally wrapping up. All right, I guess we'll stop there then. Why did this thing get stuck?